or do we first do structs?
Hey, Divindu, let me do this, and then yes to go. So hey, Coffee Compiler Club, we're going to talk about memory states, and we had a whole giant conversation on Discord on meet versus join, and when do you ever use join, and why does it matter, and lattice theory and stuff. So we're being recorded. Everyone shows up on YouTube within a couple hours or a day. And Divindu and I are talking about the next chapter in the simple project, which is going to be about memory. And we're deciding between doing arrays versus structs as the first cut going into memory. And Dibindu, you just asked me, you want to ask it again?
Yeah. My question was really, is it worth doing arrays first and then structs, or should we do the other way around?
Right. I think arrays are a tiny bit simpler than structs, but like a tiny bit. And the aliasing for the equivalence class aliasing that works really well in the sea of nodes shows itself better off on structs. So yeah, I think we can do structs first.
Okay, cool.
Yeah, and then you wanted to ask about memory state and
Yeah,
how that
exactly.
works.
I just want to get the concepts right as to how we handle memory in sea of nodes and how we do the aliasing stuff as well.
Yeah, right. Okay, so I'm gonna go pull up that. I have the talk that I've done before, but we'll focus in on the memory piece of it. And then people can pile in if they want to in whatever order they want. I'll share in a minute. Hey, Yasser.
What's up?
We are just about to do a discussion on memory state, and then you and I can go down the join versus not. I found an instance of join that totally makes sense and simple. So there is a use for join outside of cast in general compiler work, and I'll show that after. Let's do the memory thing first because Tibindu got on first here, and we'll just do memory thing.
Gotcha.
I'm trying to find the right spot to start the slide. Here we go. Okay, let me go. Where is the share button? Do that. Get York in here. Where is York? Right there. Yeah, are these visible? I can make them. I can't make them big. You have to make them bigger on your screen. I can probably shrink this around and then they get bigger by default.
They seem to be visible fine.
Okay, so and here's Darrick. So it's the main concept is we're going to treat memory like a value. Like, well, here's pi and ABC. It's just a big value. In the land of 32-bit pointers, it's 4 gigs. So it's a big fat value.
It's like the whole of memory is just one thing, right?
That's right. The whole of memory is just one thing. And then we're going to break it up into parts because we get some optimization on the parts, and the parts are exciting. But we're going to start with the whole of it being all of memory, and then we'll deal with parts in a minute. So memory is produced by start, the whole of it, all 4 gigs, and it's all empty. There's nothing in it. As a uninitialized memory state, or it's a UB or whatever undefined behavior, if you look at it, it's just a big empty thing. And calls take and produce it, and phi nodes merge it like they merge integers or strings or values or whatever. Stores take memory and produce a new giant 4 gig wad that's been modified. So
Okay, so we can defer the discussion of phi's and call, but let's say in simple, right? I want to create some new object, right? New array.
yeah,
Is that a store?
news, which I don't have any slides we'll talk about, are there are a couple ways to structure it, and I've been dealing with simpler versions, but the current state of it is you're going to have a new node. It's going to produce a new address. That address will have pre-existed in the 4 gig memory state since all of time, and no one's ever peeked at it before, and it will be empty, have nothing in it. And so generally the first thing you do after new is you store into it to initialize fields. But you'll have a new, and it produces a pointer.
I see. So new is an instruction and it produces an address.
Right. So like a new bytecode in JVM, which turns into a thread local allocation buffer, TLAB bump pointer. It turns into grab the base of the current virtual memory area and add a number to it, add the size, take the base as your pointer, and you've bumped the allocation and you test for overflow and GC and blah, blah, blah. If you do a malloc, you get a pointer back. So, behind the scenes, malloc reserves some memory, but you never saw that memory yet. It's just a wad of hidden stuff that existed since all time. You get a pointer out of a new.
So what's the outcome of new? Like, is it giving you back the memory with
No, it's
some more?
it's giving you a pointer, and the memory has always existed.
So in simple, how would this pointer be represented? What is it?
Well, we do abstract interpretation in the IR. So we'll have a pointer type. The pointer type will eventually have aliasing info. In the beginning, no aliasing, so it's all just, it's all just a pointer.
Okay, so right now we have the integer type, right?
Yeah.
And so we will have a new type for pointers.
Yeah, we'll have a pointer type. Yes.
So the
We'll
type
also
of the
have a
node,
memory type.
the type of the new node is going to be a pointer type.
Yes.
Is that correct?
Yeah. Yeah.
And
then we'll have
it's not producing a value or anything.
Well, it's producing a pointer value.
Pointer value. Okay.
Yeah.
Okay. Cool.
And then we'll have a memory type that the start will have a projection that produce all of memory type.
Right.
And the fees who take in memories will produce a memory type out.
Okay.
And a store will have a memory type in on one input and produce a memory type out. And they'll have a pointer type in and they'll have a value to store in the memory. And loads just do I take a memory, I take a pointer, I produce a value instead of taking a value.
So did you say store has 2 inputs?
3 inputs. Store has 3 inputs. The inputs are memory and an address and a value.
Okay. So address comes from new.
And the address comes from a new. Yeah. Yeah. Or prior news and or fees that carried memory, and they can be stored and loaded out. And pointers come from wherever pointers come from, but they'll start from a new. Yes.
Sorry. So what was the third thing? So there's
A value.
memory, address, and a value. Okay.
The value. Yeah.
Okay.
I'm storing 7 into memory.
And the input value always has to be like values can only be produced by loads, right? They can't be produced by stores.
Stores produces a memory. Memory is not then a value that a store instruction takes on its value input.
Right.
Now you can.
I haven't looked at the simple projects. What's the difference between memory and address?
Memory represents the place that you would put all kinds of things, and an address is a small short pointer to that memory. So a memory a pointer, fits in a register. It's 4 bytes or 8 bytes or however big your pointers are. It's a small thing you can carry around cheap, pass it, whatever. Memory is memory. It's where you store things. It's a giant gigabyte array of people's large language model, blah, blah, blah.
So in case you missed it, memory represents the whole of memory, right?
Yeah, to begin with, for what we're going to show in the Sea of Nodes compiler IR, the starting thing is that memory will be all of it, and it will be all uninitialized off of start. It'll be, you have a blank slate. If you have 32-bit pointers, you have a blank slate of 4 gigs, and it's uninitialized. You can't look at it legally until you initialize it. And that'll all happen out of the construction of the graph.
But it sounds like you can have more than one memory.
I'm going to start with just one. Later, I will break it up into pieces. The same 4 gigs or terabytes or whatever your memory size is, we will break it up by aliasing classes. And we'll talk about that in more slides in a minute.
Okay, you follow that.
Okay.
So when we create, just to recap, when we create something like new something, it's basically creating an address in this memory, right?
Yeah.
This is the pointer.
Yeah. And my example slides don't talk about new because I thought that was too obvious. But apparently not. It's all good.
So no, nothing is obvious to me.
Right. I don't know what
so we have to go into, we have
good.
to go into every little detail.
That's all.
Like, for example, you say SSA-based memory. I don't know what that means, for example.
All right, I'll get there in a second. Somebody else asked a question.
Yeah, I was thinking about this a bit, and maybe it's something we should go into later, and if so, that's fine. But I was thinking about the store object, whether it would make sense to, in addition to the 3 arguments you give it, also give it the pointer object itself so that you could figure out sort of downstream where bounds checking might be made sense to be added. So you kind of give the store object.
So store takes a memory, a pointer, and a value.
Right, but the pointer is like a computed value of where exactly. So say you have an array, the pointer is to the element.
No. So so we haven't talked about arrays. We weren't going to do in this next chapter. We're going to do arrays in this next chapter following. So in the discussion of memory going in here, pointers always point to the base of a valid chunk of memory. Now, if you want to point into the valid chunk of memory, then you have to know that the offset, which isn't discussed yet, is a valid offset. So in the case of structs, it's always valid by design because the parser gives you field offsets.
Yes.
And you name the field directly as some part of the address calculation, and you can fold that into a store if you want to. So that is a variation we haven't talked about. We can go down that path where a store has another thing, which is its field name, which it's just really an offset. So it's a string name for an offset. Okay. But if you go to arrays, you have an index, and the index math might get fancy, but you could bring the array index as an additional input to the store. But the key thing here is the store has a base memory, and then safety comes because its offset is checked somehow by the store or the graph surrounding the store. In the case of the Java version of arrays, the safety comes because the graph takes in a range check, which can be explicitly encoded in the IR, and then it can optimize the range checks, and it does, and it's important to do so. Okay, but you don't have to optimize the range checks. You could demand the store takes a base, and if it's an array store, it knows it, and it takes an index, and it does the safety check itself.
Yeah, this is sort of what I was thinking about. But yeah, I guess there's different ways you can do it, right? So if you put the range check into the IR, then it can be optimized. And if you include it into the node itself, then either you have to generate that IR later so that it can be optimized, or you just don't optimize it.
Right. So under the theory that you're intending to optimize, at some point you're going to drop it. So in the land of C2, I dropped the safety into the graph, out of a node and into the graph. So out of the Java bytecode, the Java bytecode says, I'm like a node in a graph. I'm a store into an array. I include the safety check in the store bytecode. I exploded that out into its parts. So the graph always includes the safety check, but it's separate parts. Now I can optimize it.
Yeah, I think that makes more sense.
Okay.
Okay, thanks.
But
Sorry.
are we saying that store can then have 4 inputs, right? Memory, address, offset, and value.
Yeah, there are multiple ways to skin this cat, right? So the design that you just said is the one where the store is responsible for its own safety check, but then there's no opportunity to optimize the range check. In the land of C2, where performance on array math was important, I wanted to optimize, so I went to the 3 input version, exploding the store that the user wrote directly into a range check and a store up. And then the graph always contained the safety check in the graph, but not in the store node directly.
So that's an instance where 1 bytecode coming in could produce actually quite a large number of graph.
It produces several.
Yeah.
The count is something like load the array length, compare against index as one compare op, an if branch. On the good side, the true side, you carry on to the store, and that was control flow. On the false side, you jumped to a fail. So in Java, we would call that a de-optimization. Let the interpreter do it. He'll throw an exception, blah, blah, blah. For our purposes, for simple, we can just declare it a panic. You range checked, and I'm halting your program. So that count. I'm heading.
So you're saying spell out the range check, right, in the IR.
Yeah, it's easy to spell the range check in the IR. And then immediately the IR easily optimizes a bunch of things, like that load of the array length. That happens right away. And
so
everyone
for structs,
does it.
We don't need that, right? For structs, we don't need this range check.
Yes, that's correct. For structs, there's no expansion. The offset is either encoded in the graph or encoded in the struct. I've gone both ways. They're roughly equivalent. Eventually, as you head out toward the back end, you generally encode it in a machine node as an offset. But while you're in the middle of sort of the idealized version, if you have a store to the name field of a struct, then the word name shows up in the store as I'm storing into the name field. And that's totally fine. Later, you explode that into a add 14 or whatever the offset to the name field is. And you hand that off to your machine matcher, who promptly folds it into store at address plus offset, because everyone does that. There's another hidden thing here, which is I've kept the pointer explicit, not like a pointer in the middle of an array or middle of an element. It's a base. That's because I can do GC, because I know where the base pointer is. Now, when C2 goes through large striding memory array accesses, he will make what's called a derived pointer, which is a pointer directly in the middle of the array. But he flags it special for GC purposes, and he has the base, which he always kept separate. So he hands the GC both the base and the derived, and the GC agrees to move these two values, preserving their offsets. But it's important that he has access to the base.
Right.
So if you end up with a function that you've separately compiled, and he takes a raw pointer into the middle of a struct, you've lost the base. You can't move the struct now. You can't GC on it.
So I suppose a derived pointer takes the base pointer as a def.
By the time derived pointer shows up, it comes from, it comes from some very early math that, prior to loop, which said, I started with a base with an offset, had the base, I skipped marking class and length, plus whatever the user's lower bound was, and I have this number, I hit a phi function. Then in the body of the loop, I've said derived plus equals 4 as I step the pointer 4 bytes along. So when you're looking at it locally within a loop, you don't see the base directly. But it's 100% guaranteed that I can roll backwards through the graph and find the base.
Okay.
And when I have a save point in this loop, so it's no, I will have the save point will have the base as one of the live values, because that was what the interpreter would have asked for. So the interpreter state captured in the dopt point in the middle of the loop or GC point in the middle of the loop will have the base for the interpreter plus an index. So typically the interpreter wants a base and an index, and the high performance computing Fortran code wants just the derived pointer that's walking along. So I hand him the base and I hand him the derived pointer, and the dopt code knows to subtract the two and get the index for the interpreter. And he does that math under the hood somewhere, and then he hands it off to GC. And then when it comes out of GC, he reverses that and says, well, I'm going to add the, index scaled plus blah, blah, blah. And then I'm back to derived. And then I, jump back in the code with perhaps everything moved.
Okay,
yes,
so
but SSA-based memory. Sorry, go ahead.
Yeah, just before you go into there, store. One more question about store. So store, say you started with empty memory, right? And then you've done a new, and so you've now got an address, right? For something, for a struct. Let's say this struct has two fields, X and Y. It's a point, right?
Yeah.
Now I do a store on this address, right? On X, let's say. Now what your slide says that we produce memory from a store. So what's the outcome of store here?
Okay, so in the land of no aliasing, all structs alias everybody and no one can tell them apart, and you get all of memory back out. As soon as you bring in aliasing, we're going to go to what's called, and I have slides just coming up here, an equivalence class based aliasing. In the land of equivalence class aliasing, things in the same alias class all alias to each other. Things in unrelated alias classes never alias. So if you look at historical compiler aliasing work, there's always this may and must kind of concept where sometimes they alias, sometimes they don't, and sometimes you're not sure. Okay, in the equivalence class version, there's never I'm not sure. It's either always or never. And then I can represent that directly in the graph. In the case of your guy with your point, with your X and your Y, those are two different fields. I will give them two different alias classes. So a stored X will never update a field Y, and it will only produce that slice of memory, which is point.x. It will only
So
take in that slice.
how do you represent the alias in CF nodes? Like, what is the,
Literally,
is it a new node? Is it
well,
a
I'm going to
type?
show you. We'll get there. It's going to start from the start, where the start, instead of producing all 4 gigs of all of memory, will produce all the point.x's there will ever be in all programs as one node, as just like the 4 gigs for all of memory. Instead, it will be the 4 gigs of all the point.x's that will ever be, and all the point.y's that will ever be, and all the person.names and person.ages and person.style. These will all be initialized at start, and everyone will be sliced into independent graph pieces. And after that, there's nothing about aliasing in the graph. It is done at construction at the very start of the world, maintained by the parser sort of trivially. We'll show that happens in a minute. And then you have a graph that you just do normal peoples on, and that's the aliasing is baked into the graph. You never have to maintain alias info ever again. And again, that's coming up. Why don't we go there and look at it? People have seen this here. Memory, the peoples will work the same. I'm going to show examples. I'm going to do equivalence class. And as I mentioned, it's going to be directly represented in the graph as the last few lines on the slide. And it comes for free out of the Java type system. Well, I'm hoping that simple has roughly equivalent type system to start with, and it'll come for free out of that type system as well. As long as you're strongly typed, you get it like for free. So here is more on equivalence class aliasing, and I didn't do a lot of slide time here, and maybe it's time to update the slide. So it's broken up to these equivalence classes. There's an always or never. There's a never, a maybe. Here's an example with animals, and where's Cameron with he hates cats and dogs. Here's Arthur. He probably has seen this. So under this model here, there's a legs on animals. It never impacts a cat's meow or a dog's wag. So those are 3 different fields. They'll never alias. Even though the meow and the wag are floats, they're different fields. They'll never alias. However, cat legs and dog legs do alias, unless animals abstract, in which case there's never an animal that crosses between the two. So it's dog legs and cat legs are again separate.
Did you say that the aliasing rule is field level? So for example, dot legs will alias with any dot legs of any struct.
Animal.legs will only alias against things that are animal.legs, not
okay, so it's type plus field.
Yeah, it's struct.field. Yeah, class.field. Yeah.
Okay.
Including whatever your class hierarchy is, wherever the field shows up in the hierarchy, that's the level of it. Which, like I said, for structs becomes immediately easy and obvious, and you get great aliasing out of it.
So this aliasing information is part of the type system?
No, it literally is only in the graph. And that sounds maybe a little odd, and you will get, it is useful to have subtyping types on pointers if we go there. Like at the beginning in simple, we have raw pointers, we don't know anything about them, but then we're going to turn them into pointers to structs, and a pointer to a person will never alias a pointer to animal, but that comes out on a field by field basis just for free. So the only time you talk about person is you talk about his fields, and they'll never alias. Okay. The graph will have them separate always as separate nodes and edges. They'll never cross each other. And then there's no other type info per se.
So when you say that, are you saying when we created this new object, right? If it was struct point, so that pointer will have a type saying it's point?
I typically carry that in there, and it's usually recorded as an alias number. So I could do bit vector alias things at a later date. And there's some lookup that gets you back to, class point. Yeah. But we could just put the class point somewhere. The class point needs to be shared because it has an X and a Y, and if you have large structure with a lot of these. And so that usually shows up in the type system, but I don't use it during the construction. Let me get this correct here. It shows up in optimizations where you're mixing pieces parts. And it doesn't show up if you have a really simple, I have animals, I have people, it's C, there's not any inheritance at all whatsoever.
Right.
If I make an animal, it's never a person, there's no class object, right? If you're in that kind of a world, you don't need the types to carry anything more than just, here's the number of fields and their offsets when I got there. In the
So
land
literally
where,
translate the types into some kind of alias numbering. So for
yeah,
example, let's say I have two types, point and circle, right?
yeah,
Point could have some index, say 0, and maybe X and Y will be 1 and 2, and then circle could be 3, right? Like
yeah,
it's like
and
separate
radius
from,
and diameter and all that kind of stuff. Right. Yeah, there's some numbering scheme, and it's usually done on the equivalence class level, which would be on the field level.
mm-hmm.
So 1 and 2 are point at X and point at Y, but I don't need a thing for point because I don't have ever a concept of I have a point that it's going to alias with a circle because they don't by construction.
Right. So you only need the aliasing per field
Yeah. Now, if we
number.
get to the land of where we have like a Java object that is the root hierarchy of everybody, and everybody is subclassing, as soon as you have subclassing, you do in fact get these finer granularities, and you fold them into the type system in sort of obvious ways. And
So
then,
thinking back, then when we construct a new object with a new instruction, we need to have this alias information, right?
yeah,
What's the alias number?
yeah, we go, the parser will have a table that's kept somewhere that maps alias numbers to types typically, because the type system will get used to do this as soon as we add any more fanciness to things. So we're going to head to a spot where we're going to want to have this type information around, but we won't need it for probably this chapter, but a short chapter thereafter, we'll definitely need it.
Right. And let's imagine that, I created a struct point and I assigned a value to X. So now I've got a store instruction, right? Which
Yes.
which the result of the store you're saying is now been tagged with the alias X.
The store, right? Yeah, the store has the field name in it of the X field, and that's and his pointer comes in with knowing that he's from an alias of point. I usually don't have to put the alias number in the store. I put it on the pointer that comes in, because as soon as you have subclassing, you have point 3D and point 2D, and the X field is the same for them both, but whether it's a 3D or a 2D pointer depends on what your pointer you passed in.
Right. Okay, so now I'm trying to understand what happens now if I want to assign Y a value as well in the next instruction, right?
Yeah.
So is that an independent store instruction from with memory as the input?
Yeah, it's using the Y memory for input, so it's not the X memory. It's using a pointer, the same pointer from the new, and it has whatever value you're storing for Y.
I see.
Why don't we roll forward? Because these things all show up in this examples coming up here.
Okay.
And you don't have
So
point
it's
X
not
and
one
Y.
memory per allocation.
Yes, the allocation, the new gives you a pointer and sets aside some memory. It doesn't give you in the graph the memory that got set aside. And the assumption here is that all points, all point X fields, all alias with each other. So as soon as I say I have a new point, it alias with all the old points, but the X is never aliased with the Y's.
So a way of thinking about this is that, like, if I've got an X alias and a Y alias, the X alias represents all the points in the global memory where there happens to be an X, and it's just sort of randomly distributed, say, in that X memory, but it doesn't actually matter the specifics of where they are. You're just saying that whenever I've got this thing, it represents that I've sort of got all the X's, and it's sort of as a lock on all the X's. And then I've got another one that's Y's. And so I can, as long as I'm using the X alias, I can load and store from any X, and I know that I'm not going to be, say, if I have two pointers which are the same object and I'm loading and storing from the X in some order, they're not going to get, their order is not going to get messed up because they're
Stores are
always
unordered.
strictly ordered. Or they're like, if I have two pointers to an object, but they're actually the same object, and then I store to one pointer and then I load from the other, I will get the correct, or I will always get the correct answer because that X memory alias is sort of keeping them ordered.
Yeah, X, right. Within the X fields, you force an ordering by single threading through the X memories, the point.x memories. Yes.
Yeah.
And then a bunch of peepholes
that
apply.
happen? How does that happen? For example, if I have point.x equals 1, and then in the next line, I say point.x equals 2. So now, obviously, how do we thread this into
Well, okay,
one?
I exactly have a store after store peephole optimization in this example that's coming up. So that's a store after store, where you have a store that takes in some kind of memory and he produces that kind, and a second store that's taking that same memory. They have the same pointer, so it's the same object, and you have a store after store optimization. And their store after store, you can peephole that, and I'll show an example, and you throw away the first store because you just stomped it with the second store.
Right, but what's the input to the second store before you optimize it? Like, what's its
It's the output of the first store. This pattern
and
shows
how
up. If you let me get there, I'll show you a graph pattern.
Yeah, sure.
Yeah, I got it. I mean, we're excited here. So, all right. In this example, instead of points, the thing we're going to hack on is the iterator. And that's because somebody wrote a Java program that said, for the A's array. Wherever your int array came from, I have some piles of ints. So I don't have a point object, I have an array of A's. I'm going to do aliasing things with it. And that expands under the hood to make a new iterator right here. And then I take the iterator and I bump the X field in the iterator, the index, the count, and I use it to index into the arrays. And then I just add all the elements to the array. So that's the entirety of the program. So I'm going to start by looking at a hollow shell of the program. And here I have a start, I have a memory state, and then I have an initial pointer that I got passed in. Somebody handed me the array from somewhere. And I have a loop. I'm going to iterate over the loop, and I'm just showing the loop structure, and I'm not showing anything else because the graph gets too complicated. So I'm going to filter as we go, where I'll show just the loop control flow, or just the memory state, or just the pointers, or just the whatever pieces. I'll slice the graph to keep it simple looking on the chart. So is that all clear now?
So this AS pointer at the top, right?
Yeah.
Is that a projection from start?
It's like the arg projection in simple.
Right.
We've just passed in an argument, which is a pointer to an array, which I'm calling pointer to a collection of A's. So it's a plural, it's A's. But it could be pointed ints, whatever. It's a pointer to something. Now it's array typed, and I have to have the base. So it's known that it's not a pointer in the middle of an array, it's a pointer to the base of an array. Okay. And then here I'm going to show you the math that goes to computing the sum. So there's a feed, the feed takes a 0, the sum is initialized as 0. And then the sum gets an add. You follow the blue edge to the right, down, around, back to the bottom. There's an add. It takes the sum and something else, which is a load. Well, the load comes from something that's the array base plus some scaling math, which I'm never going to show, off the index. So I'm going to grab the index. The index is 7 currently. I'm going to shift scale add the base, the mark in the class, and the length gets skipped. I'm going to multiply by 4, whatever, blah, blah, blah. That's not shown. You're just going to do the array math and load an array bit, add it to sum, and carry on a loop. That's the data flow for sum.
This smells very C-like. Are you not checking array bounds?
In this example, I am not checking array bounds. But if I were to, it will be, I don't believe I don't think I'm checking array bounds in here. I am going to pull the array length up because I use it to limit the length of the loop. So in this example, you cannot range check because I'm just running the loop to the end of the array length. In the actual expansion out of C2, you get a range check. And the trivial examples like this, I totally locally peephole the thing away. In slightly more complicated examples, I start doing more aggressive loop transforms that are not outside the scope here.
What is IS plus? What's in the
Well, that's
middle
me doing
there?
array math. So the purple IS plus here is me saying array math. However array math is, right? This is take the base of the array, that's an input, I have it, and an index, that's an input, I have it, and I have to add probably 12 if I'm a 32-bit JVM, and probably whatever 20 if I'm a 8-bit JVM. And I have to scale the index by 4 and add it to the 20 and the base. So it's base plus 20 plus 4 times index.
So we should read that IS plus question as sort of a vague cloud of nodes that we don't care about.
That's right. It's a vague cloud of nodes you don't care about. Yes.
All right.
But you know, the load should have memory as an input, right?
I'm not showing
As
memory on this slide, but it's coming up in just the next slide because I'm showing the address math and the
okay.
integer math on the sum. Let's look at the memory. Okay. So the same load appears in the bottom right. See if I can highlight it. That has a red memory edge now. So memory's red. He's got a memory input. He has his old address like he did before. So he does, in fact, have 2 inputs. I'm not showing the add on the sum now. I'm just showing memory and the index variable getting incremented. So I'm going to start at the top and go down. I have a memory state. It's all of the arrays, and as it's all of memory at the moment. I have a merge of all memory because I'm going to update memory in the loop. So rolling from there, I have a load of array plus 8. That'll give me the length, which I'm going to use for ending the loop or range check if I have them showing in the graph. I have a load off of the index object to get the index X field. And then I add 1, I store it back. Now I've modified all of memory. That modified memory rolls around the back edge and hits the feed. So I have a loop where I'm modifying memory on every state, on every trip through the loop. I'm also loading the index variable. I'm also loading the array length. I'm also loading objects from the array. So there are 3 loads in one store. And I'm kind of stuck because I can't optimize very well, although it's obvious what optimizations should apply here, because I haven't done any aliasing on memory. So is that fine here? I'm about to roll forward. So here's the mess altogether, and the comment says hard to read. Yes, it is. So don't bother. I'm going to roll forward again. I'm going to go back. I'm going to point out in this memory only thing that the iterator's X field will never alias with anything of the integer arrays, and the length field will never alias with any body element of the array. So I want to break this memory up into at least 3 alias classes. I want to have the index field for X, the X field off the index, the iterator, X field off the iterator, blah, the array length, and the array body. So I have 3 alias classes present in this example. So I'm going to look at my start and break up memory into 3 alias classes. Iteration plus 8, that's the X field. Array length, AS plus 8. And array body plus 12 plus whatever, that's the body of the array. So these are all separate memories.
Is that like you're creating separate projections there, or
yeah,
what?
Separate projections from start, yes.
So does that mean that for all existing aliases, we create projections from start?
Conceptually, there's cheap, easy ways to optimize that we'll deal with when we get there. The easy starting path is you just explode them all out. The next most easy path is you lazily explode them out, and then you don't end up inflating memory for everywhere all the time immediately up front, and then you only touch a little bit of memory here and a little memory there and a little of this and a little of that, and you're carrying this giant wad of edges around that no one's using. So we'll do this, eventually do this lazily. In this example, we are in fact going to explode everything all at once. Now I'm going to break the graph up via aliasing classes, equivalence classes on the aliasing, and I will have broken it up from the parser directly. So under this model, the iterator.x field, iterator plus 8, remains as it was because that was the key guy that was doing things. Oh, quit that. There you go. Thank you. So the outer loop red edge is still a feed from the iteration X. And then he adds 1 to it. And he stores to it, and it loops back around to the iterator X field, keeps getting modified. But the length field does not get modified. So while the parser started saying, I have a feed because I have a loop, I don't know. And then he rolls through the body of the loop and he brings it back around. No one ever modified the array length field. So he just gets a dead empty loop. So he gets a feed that backs onto itself. And in simple do, we call these lazy fees, and we wouldn't even bother to construct them. Same for the body. The body of the array length, the body of the array never gets modified. We're just reading from the array. So again, we could lazy feed this, and again, we would not actually make those dead fees at the top. Okay, so then I'm going to reshuffle the graph and remove the dead fees, but I'm not doing anything else. So here's the graph where I have relayed out and removed the dead fees. And I suggestively have put the load in the upper right for the array length above the loop, because I'm going to use it in the loop for the range check on the trip count. And I've left the address math and the memory load in the body there because the load is pinned behind the address math. I can't hoist the load out, the body of the array out of the loop because it depends on the address math. Yeah. And then I have my index variable on the left, which is load, add one, store in a tight loop. So is that, so didn't you speak up right? It's there. So from there, we go start doing peepholes. So that was out of the graph, out of the parser directly. Like we wouldn't have put those fees in the first place because we did a lazy fee thing. So we would get that prior graph just directly. So here I'm going to start looking at things I can peephole. And in this case, there is a profitable peephole by pushing a load up through a fee. And what do I mean by that? I mean, clone the load on the two arms of the fee so that you get a fee merging two loads. And so instead of merging two memories and making a load, you're going to merge two loads off their different respective memories and get a fee of the loads instead of a load of the fee. So that's a straight up peephole. The profitability comes because I can see that this load is using the same address as the store down below. That means it's going to fold away as a separate peephole. So this transformation grows the graph temporarily and then immediately shrinks it. So it's profitable. Here's the fee. Here's the load, a fee of two loads. So here's the fee, and then I have the two loads, and they're just the same as before, except that they take their respective memories when they push through, so they have different memory inputs. But they have the same addresses as before, and their values are merged, and then people use the merged fee instead of the load. So that's a local transform. I'm going to relay out the graph, taking that right-hand load to the bottom. So now I have a sharp downward purple edge with the load at the bottom. All I did was relayed out the graph. I made no other changes. Just shove that load down when I put it on the slide. But now at the bottom, I have a load after store. And this is the transformation I'm looking for. I have a load whose memory comes from a store, which means they're all in the same alias class in the first place. They have the same pointer, which means it's not just the same alias class, it's also the same object. It's the same iterator.x field, same point.x, same whatever. And so whatever the store stored, the load's going to load. So I'm just going to, instead of the load, I'm going to take what the store stored. And for everybody who uses from the load, they're going to use what the store was storing instead. And that comes out in this next transform. Oh, here, I circle it, back-to-back store load. And I'm going to peephole. I'm going to get this. I remove the load. The one consumer of the load was the original fee. It's now using the thing the store had stored before, which is the +1. And so you can conceptually think of this program as one where I load the initial value of the iterator, I add one to the iterator in a register, and I am periodically storing it. Every time through, I store the add one. But instead of doing load, add, store every trip through the loop, I'm just doing an add and a store every trip through the loop. And I don't have a load in the loop anymore. And then we're going to do the back-to-back, or we're going to do the relayout. Oh, there you go. There's the relayout where it makes it clear in the inner purple +1 fee loop. It's just, I am adding one to the iterator as I trip through the loop, and I'm storing it out every trip through the loop. We're going to go from there. Go ahead.
So for me, this is way more advanced than I am at where I am at. I mean, I don't even want to think about loops to start with. I just want sequential code
Here,
that's
right. So
accessing, like this is like way advanced than I
I
can
think
deal with right now,
I
if you
think
see what I mean.
you're not giving yourself enough credit. I'm showing it in a loop because there's a high payoff, but this transformation doesn't care about a loop. It doesn't need to see a loop. It doesn't know. You can extract the same example without a loop. It's just, I had a fee that was merging two memories and a load, and I pushed the load up through the fee. That happens in simple right now, where I have a fee that's merging constants and have an add. And I'll push that add up through the fee. So the add from below was merging two constants that are different. But when I push it up through and I have two adds, they each get an individual separate constant on their other arms. And that allows further optimizations. It's the same transformation. Fee, add, push it up. I have two adds and I get a new fee to merge the two adds. A fee, load, I'm going to push it up. I'm going to get two loads and a fee merging the two loads. Same exact transformation.
Sure. What I'm saying is I'm not at the stage of trying to think about the peepholes. I'm trying to basically understand how this aliasing thing works and how, I mean,
Okay.
even before we do any peepholes, how do we actually construct the graph?
Okay. Well, the graph will construct as we construct it now. And the only change will be when we say parser has struct.x of some kind, he'll have to know the type that the pointer is a struct point object or an iterator object. And he sees iterator.x or point.x. He'll do his lookup in his lookup table for the alias for the X guy, and it could just be the name, the string X at the moment, and he'll throw that down in the constructed node. So a constructor for a store.x or an iterator.x store, which I'm doing right here, the constructor on the store object will say something like new store node, and I have to pass in the memory, which I got from the alias, but I got from the types, which I got from the parser looked at the type of the point that he got handed, and it'll be on the point object. And then he says, oh, I need the pointer, which I got, was looking at to get the alias out of. And I need the value, which I got because that's whatever the user wrote in their expression. And I made that store object and I added the X field into the store. So it'll be a pretty straightforward new store node, piece part, done.
So is it so going back to that simple example, so start will have two projections, X and Y, right?
Yeah.
Assuming we have the one struct called point.
Yeah, here,
right?
like I have the iterator X and the array length, you'll have a point
Right.
X and a point Y, yes.
Okay. Now, whenever we store an X, do we have something like what we have like the control node, which just like it's like a token which flows down? Because if there are two stores, one after the other, they have to be sequential, right?
Yeah.
So how do we like
that
how
is what
do we like keep track of the last store in our
yes.
current path?
The scopes will be extended to take the aliased memory slices.
Right. So
So
there is a
scopes,
conceptually a name which maps to the alias.
right. The scope will start by extending with all of memory, and then when we break out for the aliases, the scopes will expand that memory slice into all the aliases that are currently exciting at the moment.
Right.
And like I said, we can start with it being all the aliases all the time, but there's a lazy way to expand the aliases so you don't have to carry a huge pile of aliases at every step.
Right. And so the store, any store instruction looks for the previous whatever value is associated with that alias. Is that correct?
Yeah, yeah.
And that could be a load or it could be another
Now,
store.
loads do not produce memory. It'll never be a load.
Oh, I see.
It will be a prior store or the start of all memory or a fee of pointer.x fields or a
So,
call if we get to
so
call
how do we order loads and stores then? Like
directly by the edges. That is the
okay.
reason the aliasing is so good in Sea of Nodes is that the ordering is done by the edges, which is everything else is done by the edges. So there's no extra ordering constraints. It's strictly by the edges. So if I roll backwards, in this example slide here at the bottom in my circled area, I have a load. It's ordered behind the store because it takes a memory input from the store. Store has to be first, load is second. They are ordered. Are you ready for me to move on, or you want to ponder here?
Yeah, no, it's fine. I'm just thinking. I have to spend some time thinking about this, which is what I plan to do over the weekend.
Okay. I spent a long time when I was doing this in grad school with whiteboards and colored markers. If that's not obvious from how the slides look.
Oh no, and this one is a more complex example. I mean, I'm kind of even
Right.
thinking
No, I started with
beyond.
the simple ones first too. Yeah.
Right.
Yeah. I was trying to show, hey, this is a cool thing we can do. So I'm going to finish this example because it's almost done, and it cleans up nicely. So I got back to, I just did the relayout after I did the store load optimization, getting the load of the index out of the loop. Now I'm loading the index once before the loop, and I'm just plus oneing it and storing it down. So now we're going to get rid of the back-to-back stores to the index in the body of the loop. I'm going to go down and just comment how this works. So let me go back up here, start here. So I have this certain structure. I have a fee on the left, which I can highlight. Maybe it's hard to highlight here because I don't know if it shows up in you guys's. Can't. It's a PDF. I can't highlight it. I didn't do it from the builder. Okay, fine. So there's a PDF. So I'm sorry. Here's a fee. I tried to
I can see
highlight
the
it.
highlighting.
It is. So it's taking a fallen input at the start of the loop as the base memory for the iterator. It's taking a package where we've updated. The store takes from a fee, which points to himself. So that's a closed form. I'm updating a variable in a loop pattern. And that's a fairly common pattern. So we're going to peephole it. So the pattern is starting at the store, I look up to my memory, I see a fee, I look at the fee, his right-hand edge goes back to me, and his marker or his region marker says I'm a loop. So I have a store and a loop. So that's the entirety of the pattern. I have a fee, his back edge is me. Store has a fee, has me. Boom, pattern. Take that pattern, I'm just going to remove myself from repeatedly updating in the body of the loop and just say, the fees memory is whatever my input memory is. And I get a tight fee loop for the store of the index, which is a junk fee, which we'll remove now and relay out the graph. And we get this. So the only thing else I did on this picture is I said a load from the new memory of a new iterator is always 0. As part of the spec for Java, totally we can make it spec for simple. We'll have to do something here, so I think it's a good spec. And then we get this graph for tracking memory and iterator indices. And it's just, we're going to take the store memory for the iterator's index memory.
Why is that 0 and not read uninitialized memory?
Because I know that new objects in Java always give me a 0 from an initial field. So the thing that I didn't do here was show the new object constructor giving me the new memory. I gave it as from start. So I a little bit cheated at that point. We could argue that I could complicate the graph and put a new in there, and that would make me carry a graph around. It's only used at this point where I say, oh. And then if you did that, though, I guess there'd be further optimization where say the iterator's dead, throw it away. So that would be an optimization I didn't show here, but we could at this point claim the iterator's dead, throw it away. So as it stands then, I have the fee merging the iterator's initial 0 and the +1 in a tight loop, and I'm just adding 1 and then using that value for the array math. And I store the final value of the iterator. The one store takes the final value as you exit the loop and updates the iterator. And then if no one else is using the iterator, the pointer for the iterator, which is used one time in the store, will then be treated as dead. And Yasser was just talking about doing this earlier today on Discord. And then you declare the object dead, and you throw away the memory state, and you throw away the store, and it all cleans up nicely, and life goes on. I'll throw it all together, but it's a real eye chart to read. It's a little better than the original eye chart, but it's pretty straightforward. Here I've included, by the way, the load of the length for the range, not the range check, the loop check. And it's been moved over to the left. But this particular program, I can now generate code for the body of the loop that looks like, pointer plus plus, contents pointer plus plus is added onto sum plus equals pointer plus plus. It's got a nice form and it optimized well, and I can do something. So I didn't do any loop optimizations on this per se. I just did did peepholes, no special. Oh, Matt says he'll be back in a second. Yeah, then that's it. And now otherwise I have comments for, hey, but comments for the entire talk. That's the
so remember those little graphs that I posted the other day? Would it make sense to look at those? Those are simple. They don't have any peepholes, and they're the one that you gave me where the create a person objects at the name. Should I share the screen?
Yeah, hang on. The issue with those is they're on Discord, and
I've got them on my screen though.
Okay, yeah, do them on your screen. That works. I can't
Okay.
show Discord without asking everybody. That's okay.
No. So I just need to be able to share the screen.
I'm getting there slowly. I'm clicking the wrong buttons. Try it now.
Okay. So let me just make it a good size. So I've got 3 variations of this. I've been drawing, this is sort of what I do. I like think through these things and draw them. So I've got I've got one where I just start with like an all memory.
Right.
And then another one where I say, actually, what if I do it with a person?
Go back to the all memory one, because we should talk out the differences in how the graph looks so people follow.
Yeah. Okay. So this one is a function rather than going from start. So the memory is something that's kind of like a p, that's a parameter that's passed in.
Right. You're passing in a p and you're making a new p. And our question was, can we separate the aliasing between the brand new one and the old guy?
Yeah. So, and it's possible that there's some mistakes in here too. So we'll see. But so a person is passed in.
And it wouldn't be a fee, it'd be an argument.
Okay. Right.
Yeah, so this is why I didn't get this one, because you have fees here, but why do we need any fees in this sequential piece of code?
Right. He gets fees at the bottom where he says return random choice of P0 and P1.
Sure, that's an if, but
right. Well, in mine, I treated arguments and fees as the same.
Yes, so. And AA does the same thing. The arguments are basically a fee merging from all callers. But I call them arg for now. Everyone gets it's an arg at the start of the function.
Yeah, so it's an arg. I changed it.
Right.
So basically we're receiving this P0, that's this guy, and we're creating a new person. So this is happening here, and that produces the new person pointer, and that's going to have the length and address, and then the memory.
Yeah, and in your case, you're using it to slice off the new memory, and we can argue at level of precision. And your goal here was to say new person does not alias with person 0, because the new is right here, right now, and so you do need a new memory to do this level of aliasing. For what Dibiendo and I have been talking about in simple is this will be a later step. We won't have a memory there to start with, but if you want to do this kind of, hey, you made a new right here, we'll need to do a memory there.
I see.
I'm just pointing out for Dibiendo's sake, we're getting to this level, but this is a higher precision than what we've been talking about.
Okay. But here we're still doing, we're still just saying we've modified all memory somehow.
We've modified all person memories.
In fact, I've just said all memory here.
Oh, I see. You did say all memory. Yeah, you don't need to. You would. Okay. In C2, AA, C of nodes, I would not have that top memory edge hitting the new.
Yeah. So I also think I won't do this. So, but I'll just walk through this here.
Yeah,
so
let's clean this up a little bit. So you have pointer, then you have base adder. I claim pointer is the base adder. I wouldn't have the base adder as a node. I just have the pointer.
Okay. Yeah, so that's fine.
Okay, next piece, you're adding the field offset to the store, but I put the field in the store for structs, so I would change that as a store with a .name field. So in the store node, I put the name field as the constant field and get rid of the add of person.name.
So this would be like a store named store
It's
field.
no, it's name, not it's the
And then
field
you've got like that's the node is store field.
But there's a name on the field, and the field is the named field, quote name. Yeah, person.name, but I don't need person. That comes from the pointer. So I just need the name, the name. Like get rid of
I
person
see.
dot. Yes.
So like this?
Yes.
And then
Then
you
get
don't
rid of the add. Yeah, you don't need
so
the
you're
add.
just gonna point this here like that.
Right. Yep, and delete those two. Yep.
Okay, so how do you deal with you know, maybe I've got another object that has a name, but it's at a different offset or something like.
Well, it's a different pointer.
So if it's a different class or type, then it doesn't alias, right?
It doesn't
With
alias,
this name.
and those two will never mix.
But if it's person, it will always alias.
It will always alias, and they will be forced to thread through shared memory. Yeah.
Okay.
Either never or always. So
this pointer object has the field offset positions.
It has the class, which implies you're going to do a layout on the name at some future date. You don't have to pick layouts now.
Right.
So it knows it's person, right? So pointer needs to know it's person.
Yeah, pointer needs to know it's person. And then you get that from the new. Like in the land of what I originally talked about for simple, I don't need a three-way set of new pointer mem because we're not taking a new mem because we're just going to fucking alias everybody. So the new is the pointer. And the new guide needs to have the person type buried inside of it. It's not an input to new. It's just part of the news. Like pointer, it's not, no.
It's not like that.
Okay. I buried them in the node because it's not a graph piece. It's not a graph.
I see. Okay.
And that's why I don't use node edges. I would say it's the new, and inside the new top guy, I would put you're a person. You're a new person.
So let me just make this really small and stick it in there.
Yeah. Yes, it is. Right. Put it on the new.
Okay.
And in the land of I am trying to do sharper aliasing, the new produces a pointer to mem, but the new is a person type. And then you have a pointer out of the person and a new memory for this new person object I just made.
Okay. All right. So we've got a new person, and then this pointer is going to know.
Yeah, you only have the one store, but it's independent from P0. So updates on the new object until you've escaped the new object via this fee at the bottom. Until you escape it, it's all independent and they can all optimize on the single object. In fact, they'll only have the one pointer. They'll all share. It'll be store after store and load after store, optimization peoples. They'll all clean up.
Yeah. Yeah. Okay. So then
now,
go ahead.
So now instead of print P1, can we do print P0.name?
Yeah.
Because that's more interesting. Like, okay, how do I?
Well, he wrote the graph of printing all of P1, and he gave P1 the pointer, and he gave it so you have two different, that's a P0 print. I heard Debian ask for P1.name print.
Even P0.name, right? Because we just created P0.name. We assigned something to it. Now, if I want to print that.
So the IR, the parser dumbly puts out is, you said print as an argument P1.name. Well, P1.name is a load. You stick a load in.
Yeah.
And then you do a load after store optimization.
Yeah.
And the load after store optimization will just find cliff. It'll just optimize down to print cliff.
So you're missing a load there, right?
Okay. Yeah, there's a load there. It's a field. Yeah, it needs the same pointer input. It needs the memory from there.
Yeah.
But is the load, well, this is my question. Is the load does it have an input from the store?
Yes, it has a memory from the store, which I see the edge for. He needs a memory from pointer.
I
We
see.
don't use the word field because we know it's a field load because it has a name. You can tell because it has a, right.
Okay.
And in fact, when I do this with fields like this, I'll have a store class for field loads and stores, but to do arrays, there'll be a separate store and they'll share a common base store for some behaviors, and they'll do the math, the indexing math a little different. You put the load back.
There's something going wrong with my drawing program.
I
It's not
see.
letting me connect this line, but
Yeah, I see. And now the load
So-
needs a line also up to pointer.
right.
Okay,
Yeah.
so the load's memory comes from the last, most recent alias for that memory, right?
Right.
Yeah.
Because you got to track this somehow,
Yeah,
that the store name is gonna like.
This is tracked in the parser's scope objects, the way you track updates to a variable that just gets stored into.
Right.
I'm just going to replace this node. Sometimes this type of issue causes the whole drawing program to crash. This thing's on the border of crashing, so if it crashes, it crashes. But anyway.
Yeah. And now the load and store does a load after store optimization.
Yes.
You don't have to show, and you just pick
Right.
up the cliff.
And then eventually we would just point this to that, to
right,
cliff.
point directly to cliff and right.
Yeah.
Okay.
Okay.
All right. I think this is helpful because this is what I was trying to understand. How do the basics work?
Yeah. And if we move on to this one, and it has the same sort of mistakes that we fixed before, but I think we can ignore that. But here I just say, well, it's actually the memory is a person, but it's not aliasing. It's sort of like all the fields of the person, but it basically operates exactly the same way.
Are you attempting to keep the new person separate from old persons or not?
No, it would be like all persons.
Okay. And under the land of all persons, you don't need the person alias underneath new.
You don't?
Because that says I've made a new memory for P1 specifically, and you're not saying that. You're saying it's all the same. All persons are persons are persons. As soon as I have a P1, it aliases P0. You have to, go to the next step from there.
So this line can actually just point straight to there.
And you drop that one, drop that person highlighted. Yeah. Right.
So.
And then because pointer from new is exactly there, I just get rid of the pointer. You get rid of the base address, you ditch that. And then you get rid of the offset, and you just need the pointer into it. We're fixing things we fixed before, so just
so let's not bother just because we already know that. So then and this print is also missing its load, but so this should have a load in there.
Yeah, and the store it has needs to. Oh, he has his point to pointer. Yeah, he does. I'd like to get rid of it because it makes it easier. But you can still do a load after store here optimization, even though you haven't broken up separate peoples, because you have a pointer that's directly there, and there are no other uses of the store. So there's another hack that has to happen here that I haven't talked about, like push the store up so you get a little bit better layout.
Yeah.
Oh, I didn't
really annoying that this acting bad, but okay.
Yeah.
So
all right. So here, because the load comes from a store of pointer and you have a store in the pointer and the objects are all the same, you can in fact still do load after store optimization. This one still applies.
Yeah.
But in general, you'll have other stores with other pointers and then they won't apply.
Right.
There's something in between.
Yeah. If I stored something into P0, then I wouldn't necessarily know.
Right. You wouldn't know. Yeah. And the example to your left, the whole slide to your left, you would always know. And
but
this example, as soon as you have a separate,
with this load after store, even if I had some other stores happening to P0, if this load happened after this specific store, there I can look at the pointers.
Yeah, the thing you have to watch out is that there can't be, the load can't peek through another store to get to this store. So you have one store. So put your second store in. Your second store P0 in. And it's just a store. We know it's the name field. It comes from P0. It gets from this store is memory. Yes, yes. And the load now gets from the second store. This is where you get confused. So you need to move the bottom store up or move everything else down. You need to do graph shuffle. Fine. You know, shuffle the graph a little bit. You're doing layout. Great. Move that load down. Yes. And now he points to there, right? Now yes, that goes up to the first store, right?
Yeah.
So that load can't fold away because he's unclear which of the two stores. You didn't put a value on this store. You shortened Darrell into pieces.
Right. Because this, well, in this case, this couldn't be the new, but if I had, you know, another, like if I get rid of the new and I had a P1
same thing.
And all of these arrows were moved up to there, then I would have ambiguity because this could be the same object passed in, right?
Right. So that's the nature of the peephole. It's the load comes from a store directly and they share the same address, then it works. In the example, as you have it now, the load does not come from a store with the same pointer. He comes from a store who one is pointer 0 and one is pointer 1. They're different pointers. She can't do it.
Yeah. So you look at the immediate store and you can optimize if you have good graph there, but otherwise, no.
So the general theory on this kind of optimization is because the aliasing is so strong, I typically do have adjacent store loads that are directly optimizable.
Yeah. So then the next one I did is where I've actually got like person age. And so here, I guess I've,
again, if you're having the new,
this.
Yeah, the new is either you're taking the sharpness of the new versus all memory, or you're not. And if get rid of person age there, yeah, there it is. And you get rid of the base adder add, and you put the offset into the store, and it cleans up a little bit. But yep, sure enough.
Right. So that's okay. So it's surprising to me that the new doesn't. So if in the all memory version, the new does have to create a memory.
No.
This one doesn't either.
No, it's when you have when you're attempting to do a precision level that says a new has not escaped. Either it escapes immediately or it does not. If it escapes immediately, you don't need the memory because it's just part of the bulk memory for the new.
Right.
And maybe broken out field by field by field. But if you want to do I have a new object, it doesn't escape yet, now you need a memory.
Right. So there's not really a need for projection here then, right? The new is the pointer.
Yes. And that's, in fact, how I do this when I'm doing it this way. The new is the pointer. There is no projection. You just get rid of it and you just fold them up into the same thing.
Right. Yeah, so these all move and the thing is not cooperating, but it's so funny because this drawing app works so good most of the time, but today it's really being naughty. It's probably because I have 50 tabs of it open.
Oh, it's on your browser or something?
No, it's a native app.
Just separate things, yeah. Well, it means it had some leak memory, something bad somewhere, and yeah.
Yeah, exactly. Usually it will crash fairly shortly after starting to do stuff like this.
Right. Back when I was writing my thesis, I was using Microsoft Word, and it worked well until it started to crash. And then I realized that it had been broken for a while, and I didn't realize it. And it was broken from some time, had auto been saving brokenness.
Oh, great.
And so I ended up having to keep like rolling 10 versions separated by, 10 minutes to an hour a piece for a long time back, because when I finally discovered it was in fact broken, I might have to roll back a long time. It really sucked. It was back then, Microsoft Word was not up to writing a PhD thesis.
Yeah. I used to work with Microsoft Access and I had the same kind of crazy things where the database would get corrupted and you had to go back. In fact, I had a whole process that automated reconstructing it from a new database, and sometimes it would still be corrupted.
So I want to point out something else here. So I said at the start, we got person age and person name, and you're showing them up there. At the return, you have to take them all.
Yes.
All those aliases at the start, all get picked up by return too.
Yeah, I've got those here.
And since person.age is neither used nor consumed by anywhere in this particular program,
gets peeped out of here.
Right. There is an easy way. Yeah, there is an easy way to make it lazy, and you would peep this one. You just peep it out of there. Yeah.
Yeah, okay. There's an
I
easy
have
way to
one
make it
question.
lazy for function arguments, for function.
Let do ask his question here.
So my question is, when you're not accessing a field, like you're printing P1, so in that case, do you need a load, or do you just say I'm passing the pointer?
Well, okay, so what does the function P1 take as an argument? Suppose it takes only primitives. Well, you can't pass a pointer to it. That's not a primitive. You got to load. Suppose it takes a pointer, but then internally it's going to break it out into all the fields, use reflection, discover all the fields, what the fuck's reflection mean in the graph, blah, 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 and print everything. Well, it has to take in then the pointer, but has to take in all of the aliases that pointer points to, because it needs to read all those memory states. So in the example where print is a special magical function that's not really a function, but it will peek inside of things, it still needs the memory state. In the land of print is C's printf, it's a totally generic thing. It's going to take all of memory, like all calls do. All calls take all of memory. And so you have to have an efficient, cheap, easy graph way to bunch up all the memories to hand them to a call, and then split them all out again after a call, because calls happen. They're common enough. And so that's getting into a discussion about how you lazy blow out extended counts of aliases and such.
I see.
But we don't need that for the first cut of memory.
No, because we don't have function calls.
And we don't have function calls. Right. So we're getting there, right? It's all coming together. We're quite far along, actually. I think we get memory and we get function calls. We have a usable language. We're not far from a really usable language.
Yeah.
There you go.
So what's the mechanism for lazily including these?
Oh, I would start with a bulk all of memory, and if a store shows, if a load reads from bulk, he's reading just the slice and it's kept lazy. If a store comes along and updates a slice, then he reads from bulk and he makes a slice. Now I have to carry the slice forward for all time. When I hit a loop and I don't know if I'm going to have stores in the loop or not, then I do like I do with the lazy fee thing. I have a lazy memory fee. If it explodes into a real fee, it does, and then it explodes again into a sliced fee. And that happens at the time I close the package on the loop. I'll update the slices to fix that. You can also do a merge join or a merge split memory pointer, a node game where every memory starts out packed as dense. If I want to see a split, I'll put a split node in, and the split takes a bulk memory and makes as many parts as I want, most of which will be not looked at. And so he'll have a bulk edge, which is all the things I didn't mention, and then I'll have breakouts for person.age, person.name, iterator.x, point.y, whatever. And the merge will take the inverse of that, and those two will always be balanced, and it's a node in the graph. Now, having a node in the graph that does that, I can do peepholes to widen the precision range. Like it's where the precision is split out in some narrow piece. People outside of it get bulk memory. They're lost and confused. They have poor aliasing. Correct, but poor aliasing. If they butt up against a split or a merge, they can swap with it and go inside the split merge, single entry, single exit region where I have more precision. Now they get more precision. I can do more precise, same peoples as before, but they're on more precise edges. You clean up that way. That's a game where I lazily explode the precision. C2, I've played with that in AA some. I don't know how well it works out in large scale. C2, I played the game I just mentioned earlier where every time a store showed up, I got precise on that alias, and I kept laziness up until I saw the store, and then I went back and patched in the lazy precision at every loop header. As I unwound the parser, as he came back to a loop header, he went back and said, "Oh, geez, you went precise here."
Yeah, my first cut of the compiler, I tried something like that, but I think I did the insane version of it, because in mine I had this concept called all state, which was which was this all memory
Yeah,
basically.
it's all memory. Yeah, right.
And it would, but then I didn't have the concept that you could use it unless it had been fully made precise. And so then I had all these extremely complex peepholes working their way through loops, through call sides, through everything, and expanding it out, which was really expensive. And then, you know, it would also peep them away and like get rid of, you know, aliases that weren't used or like weren't used in a function and stuff. But it was all like not lazy, and it was so much work and so buggy.
Okay. Well, that would be my split merge example, where instead of splitting one by one or whatever you ask for, you split them all at once.
Yeah.
And you merge and then you optimized away. No, I think for simple, we should start with the lazy. I think it's a reasonable approximation. So I said that for C2, that was what I was headed for, or I did at some point. There was another version, I think the earlier version, where I made a separate pass with the bytecodes and I got all the aliases collected. Then I split all aliases up front. And then I said, no, I had to be lazy. So then I went to there's a bulk.
Yeah.
But I knew when it came to a loop that I had to put in fees for all the aliases. So I put in fees for all aliases at a loop header. And then immediately they folded up when the loop closed because no one ever talked about that alias. Fine.
Yeah. What I ended up doing, and it was a huge improvement, like in terms of simplifying my whole code base, is I just went with explicit aliases for every single thing from the start. I just figured out what they are and it would add them into the start node, and like, yeah. So it ended up being far simpler.
You want to stop share here?
Yeah, sure.
Well, I'm looking at how I call. I guess I could force.
So it worked okay for me because I overall had small programs. So the fact that I had thousands of memory edges, it slowed things down, but
right,
it was way faster.
Yeah, C2 speed counted. I couldn't do that. I tried that. I got there and I said, no, back off.
Yeah.
The lazy thing was okay. It worked out. You had to be a little smart when you re-expanded later, but for nested good control flow, you're only expanding out at loops, and then you decided to visit all the consumers of this fee that you were hoping was lazy but wasn't, and you found them all by their aliasing, which you could tell by looking at the pointer values, and you broke them up onto the correct fees, and then you got your precision back.
Question, actually. I guess the new in my example also doesn't even consume the memory, right? Like it's not producing anything. It's not changing.
Well, if you are doing the game of all the memory is, you have this funny thing here now. If you're doing the all things alias immediately, they escape immediately, then you don't need a memory state there at all. They've already escaped. They just bypass. He doesn't produce a memory, he doesn't consume a memory. If you're doing the thing where the fee is making a new pointer that has not escaped, the memory is precise, you've made a memory node for precise memory, so you single thread the loads and stores correctly on that one object. When you escape, you have to merge their memory state into the main memory state of all of those things. Now you need, not shown in your graph, you need a memory merge that takes the final state of all stores into that private object and merges them into all the stores of all the other objects. And now you need a memory merge, which is just the memory merge I talked about earlier when I said precision, split, whatever. It's the same merge. Well, semantically, I guess it's slightly different because it's the same concept. You're just merging the memory states. It's not a fee merge. It's a bulk join merge. It's not, so there's no control flow gating one edge or another. It's these two memory states are now confused. I can't tell them apart no more.
Yeah.
And that would happen as soon as you did something with the memory, with the pointer, that you can't tell what the hell's going on. And that includes storing the pointer into some other structure that you don't know who the hell's touching what's in that structure. So in the land of, I don't care about concurrency or other, the memory model allows me to cheat here, which Java does in this case. The act of storing itself means it has escaped on the alias side, but not necessarily visible to other threads, and you can delay, that's all fine. But the next time you do something with that shared memory, you don't know, the shared pointer, you don't know. So I don't have to merge P1 and P0. It suffices to store P1 into some global and then make a function call. And at that point, P1 got stored to a global, it's escaped because the function call is going to read it, has to have the merged memory. I must merge the memory before I pass it into the function call. So the private memory no escape guy has some more complicated rules about him. And that's why I don't think simple will start there, but it's not a hard place to go. You just have to watch all the little edge cases. Okay. Divindu, you feeling a little better about what's going on? No. Or he's not at the mic now. He's off crying in his coffee. No. All right, fine. Anything else? I know Yasser and I were going back and forth with Jules on lattices, but I think you and I are on the same page. And I don't know, Jules got himself figured out.
I think so. Yeah, my basic I guess the premise was, first of all, we do need top, we do need bottom, and I think we pointed out why. And then join is relatively cheap to implement and comes up in certain cases, like the narrowing case, or as you mentioned, the GVN case, where you don't want it to, like, if you had two nodes and they were like different states of being like type checked, then you don't want to like undo your typing. You'd rather keep it.
Yes, you 100% dead on. That's it. Anyone else want more detail on that one, or it's a totally separate topic? One new message from below. Oh God.
Hey, sorry, I have to leave, unfortunately. I was interested in that, but I can watch the recording later on. If you guys...
somebody has to drive the questions.
Well, it would be good to maybe if you could give a walkthrough of the join you mentioned in simple and why it's required.
Okay.
Unfortunately, I have to go, but
yeah, fine. Yeah, I'll do something here.
Thank you.
This is lattice theory,
and one I've been debating with that. You did this combination Henry Milder forward flow.
Yeah, I'm not talking about that combination.
But I often find that when I'm reading code, I'm kind of reading in the direction that time flows.
Yeah, right.
So it's a little weird to me when I run across a value and it's just like, let auto this thing. Oh, some point later in the code, it will tell you what it is.
Yeah.
Like, is it actually easier to work with that than it is to work with a purely forward flow where the compiler's doing typing in kind of the same way my brain is?
Yeah, I don't know. I use var occasionally when the types got long and obnoxious and I didn't want to type them out. And then I'm with you that, oh, I have to go. And it's not that somewhere future tells you what it is. The past has told you what it is. But you have to interpret, you have to read the expression that's assigning and to figure out what they're getting out of it. Henry Milner does it, you're right, in the future and past. It's bidirectional, it goes both ways, fine. But if I'm just writing Java code or Python or...
Right, this happens to me in my Rust code, that frequently you'll have a variable and you're like, wait, what is this thing? And the answer is, well, later in the page, it's passed into a function and that function has a typed argument. Well, so it learned what type it must be because that function it got passed into, and then it flows backward in time.
You're like JavaScripting yourself now. JavaScript is weakly typed in various kinds. I don't know. It sounds a little more trouble. Yeah.
I mean, it's strongly typed. There is a clear answer there.
No, JavaScript is not. It's strongly typed the way Python is.
No, I'm saying in Rust, it's strongly typed.
You're getting this out of
Rust.
But
often the type comes from the future.
Okay.
That it is actually what this variable will be passed into later that determines what the type is.
What the type is. Yes. Anything with Henry Milner can do that. And I don't know how it feels in Rust. That's a good point. Don't know. All right, let's talk about it for Divindu's sake here. Blah, 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 lecturing to a blank wall. It's painful. Sorry, you guys aren't blank walls. That's not fair. Yeah, there's this lattice. We've talked about it a bunch. It's this top, middle, bottom is the easy version, but there are much more extensions to the lattice that come from all over the place. The properties of the lattice that are exciting here make a monotone analysis framework, which gives you the property that there is a single best answer. It's well mathematically defined. You can get it in linear time to size a program. And in fact, you can get it with a work list algorithm, which doesn't care what order it visits nodes. So there's a highly efficient, easy to write work list algorithm that iterates quickly to a fixed point. So those are the properties you want. Backing up from those properties, you get them from a lattice that has got associativity, commutativity, a couple other things. You typically present as symmetric. I think there's historical reasons for it, but then I kept finding uses for join, and so I went with symmetry. If you don't do anything with a backwards flow, which would be a cast, and you don't do some kind of peepholes while running a pessimistic guy, I am not certain you need a join, and maybe you could come with a half a lattice, a semi-lattice. Given that I am doing peepholes while I'm doing type propagation, I want the strong theory on the type propagation, I need a join. Given I'm doing casts, I need a join. Okay, so I have a join. What the hell is a join? Well, it's the backwards version of a meet. So meet in a lattice is typically draw a lattice as a Hesse diagram. There's some top, there's some complicated stuff, and it meets just at the bottom. In order for the lattice to have a join, the lattice has to be symmetric. So it looks like this. Given that you have a symmetric lattice, you can define it from either a combination of meet plus join or meet plus dual or dual plus join. Any two of those three define the lattice. Because you're symmetric, dual is usually trivial to implement. Like you're writing a lattice as a piece of code, it's this trivial thing that flips a bit. It's not quite that trivial, but it's close. So I just write meet because conceptually that's easy to think about, and I write dual because it's easy to code, and then I got join for free. Okay, so I'm writing not much more work over meet to get duals and joins, and I'm done. Now I can do joins. So now let's talk about where we use joins for. So the obvious ones you do with an upcast, where you say something like, if A is a B, then inside this if block, I'm going to cast A up to be a B type. That's an upcast. I have lifted A's type from unknown some object to person because A is a person. That's a join in the lattice because anything I know about A beforehand remains true, but I also know that A is a person. And so you do a join so you don't lose any information about A while making it a person. Same for null checks. I have some unknown pointer, it's null or not. I say if not null, do pointer dot field things. Okay, that's an upcast. Everything was true about pointer before remains true. Also, I know it's not null. That's a join. When I do the global value numbering,
can work on anonymous things also, right?
I'm sorry.
Do you have to go up a type hierarchy that was declared, or can you just be like, hey, from one side I've got a struct with A and B, and another side I've got a struct from B and C. So when I hit this line of code, if I say thing.b, that's fine because there's a B on either side.
Yes, and that would be if I was doing some kind of duck typing game, which happens totally.
And null is basically now just the struct that has no fields.
It has a struct that has a B. That's usually done out of Henley, comes out of Henley-Milner. From forward flow typing, I would say, I have a point XY, I have a point YZ. These are two different types. I can't merge them, even though they have a common Y field. In Henley-Milner, I would say, I have a point XY and I have a point YZ. When I merge them, well, they both have a Y field. So sure, I got a Y field. Now, when I go do code generation, I have to do layouts. The Y fields have to have similar offsets, or it's a bitch to do lookups. And that makes a more difficult code gen situation because I get conflicting constraints. You can't always do layouts that are compatible. So I don't know, how that plays in efficient, nice code like you might think, but it only comes out of Henley-Milner. You do forward flow typing, you don't get that game.
But that's all about getting an API. When I'm trying to decide, like, hey, I hit dot, what should I autocomplete? I just need the API information of,
yeah,
hey, what can you call here?
Yeah, you could flow that. So
Because I'm always annoyed when I have to write the struct that's like, if you're the first type, call print. If you're the second type, call print. It's like I have the exact same code in both blocks, but I have to match it to call it. It's like, no, if print will take either of these, it should just
but because
work.
print takes a shared common header. But you can get that directly. If I have a I have a point XY and a point 3D and I merge them, well, I have a point XY now. And I just, as long as I don't print Z, I'm all happy. And now I can go do XY printing. But if I hand it to print, who's the general purpose print, he takes an object. Then he does, oh, well, you know, I'll lift you up to object. Point XY is definitely object. I'll take an object. Done. So print's all good. Because there is a class hierarchy with a shared common root, and he takes that common root. And he cheats using reflection to go upcast everybody. He upcasts internally.
I was going to say, shouldn't print not take a common root, though? He just takes things that have a toString that takes no arguments and return a string.
So the way it's done in Java and C++, he takes a common guy. In some other version of the world, you might say he takes an interface that has a toString, which is another way of saying there is a common root of everybody who takes toStrings. But now you're getting the types of interface types, which I wasn't going to do with Lattice things, but you can play games and get it to happen there too.
Yeah, I assumed an interface was always a point on the lattice.
Yeah, it's not terribly. It's more like what Hindley-Milner does. So I usually reserve the lattice for things in a class tree like hierarchy. And then I can say strong things about them. And interfaces are basically object plus a property from the lattice sides, and from Hindley-Milner sides, they are precision of
my gist was that in general in AA, people were gonna, you just write your function and it figures out what the types it's willing to take is based on everything you called on the things you took in.
Yeah. But that's Hindley-Milner going to town, and the forward flow typing adds some precision in different ways. It funnily adds precision on who can be called. I get call graph sharpness, which immediately turns into, or I get the dead code thing. There's a bunch of sharpness that comes out of the mix of the two, but they're in different.
That's why I'm interested in the idea of, can you name types but not actually define them anywhere? And be like, the only constraint is that in these three places in my program, the type must be the same. So all of the constraints that apply to any of the three apply to all of the three.
You know, in the land of AA here, if you don't give a name, he'll just infer the layout. What do you give a name to? He'll just infer.
Right. I'm saying, what happens if you have a name that only ever appears on the right side of colons?
I would. That should be totally doable.
That should work.
That should work.
And, you know, it'd be nice if I mouse over it and it tries to give me some kind of definition of what it came up with as the list of constraints. But
that's right. That is what you get by default if you don't use a type at all. I have three things. I use them all together.
The difference is what happens if I put the same symbol in two places. So I say I take A, which is a thing, and I take B, which is a thing.
Right.
And now I want all of the constraints that everything that happened to either A or B in my function should be constraints on both when they get past it.
Right. So if you were to write that in code, you would write your normal code, and then without writing the A's or the B's, you would simply take the things that you would write with A and the things you write with B, and you mix them up and then do the same things to them. This code doesn't have to execute, you just have to mix them together and do the same thing. That type is the type of whatever A's and B's together do, and they're forced to be the same because you merged them together.
Right. I merged them together by naming them, or I just merged them together by using them?
I think you'd have to use them. You would confuse them with a random fee. If random A or B, now I have an AB thingy, whatever the hell AB thingy is. Well, I can do A things with AB thingies. I can do B things with AB thingies because I then have to use them as A things and B things. As soon as that happens, you don't have to have that runnable just to be past the compiler. He has to merge them into an AB type. And so I'm giving you a way to write this is extra code. Now there's a shortcut that says, do this behind the scenes. Don't make me write the code for it, where I say, Okay, I have an A thingy and I have a B thingy, but I want them to be the same, so I'm going to declare them as an AB thingy with a type annotation that said colon AB on the both of them, and now I'll give you a colon. Yeah, so that should just come out. That should totally be doable. And now we're talking Henley-Milner, which is fine. We're done with types. I mean, with lattice theory, I think. We get to where we're going to do is asking questions. We'll go around again. So if you're listening,
my only problem is I still don't have a intuitive understanding of what a dual is. What does it mean for something to be of type dual 3?
3 is on the center line, so dual 3 is 3. It's a mirror.
But dual of uint 8 is not uint 8?
It's the dual of uint 8. That's correct. It is not uint 8. Uint 8 is not on the center line. So the lattice is top, bottom, constants. Oh, but I want uint 8, so I have ranges. So it's top, constants, bottom. Down here, I have a range of 0 to 256, 255. There's a dual range.
I have a actual picture of lattice up on my screen right now.
Oh, well, share it. See how bad it is. And the one way to think about the dual is the way you think about top is it's everything. The compiler, it's undefined behavior. The compiler can do anything it wants with that value. You've read uninitialized memory. The compiler can pick what you're reading. He picks what he wants.
So the way I've been thinking about it is that the one that's close to top is any int 256.
Yes, any, yes.
And the one that's on the bottom is all int 256s.
Yes, that's how I write it.
The dual is the difference between any and all.
Yes, that's how I write it in AA. That's how the names even of the variable of the type.
So 3 is its own dual, because if I say this is true for any 3 or this is true for all 3s, it's 3.
It's 3.
There's one value.
Yeah. Another way maybe it helps is that top is the compiler knows it's all constants all the time, all together, all at once. And for uint 8, it's all the uint 8s all together, all possible uint 8s all at once. And when you fall to the bottom one, it's this specific one I have to compute. One is over constrained. It has all constants. You must be all the constants all the time, all at once. Makes no sense. One is under constrained. I have to go compute it. I don't know what it is. I have to go find out the hard way. Okay, that didn't help. That's
so another top is any and bottom is all.
Yeah, top is
bottom
any.
is all. I called it unknown in my own system just because I felt that was more intuitive, and I kept on mixing up any and all.
Yeah,
but
fine.
Unknown, basically to me, what I treat unknown as it needs to be computed.
Yeah.
And any is more abstract.
It's the value that I can pick when I come to a loop and I don't know what the back edge is. I'm going to pick an any value, and then I'll find out what the back edge is after I finish the analysis.
Yeah. So
but when I'm done compiling, I could still have something above the line. I just pick one.
No, generally, if you have something above the line, you have undefined behavior, and you should either throw an error or you should declare it dead. It's dead, and you can get rid of it. So when I run peepholes on simple using the fuzzer to get evil code, it says shit like some complicated stuff. If what's going to be false, while some loop, but the loop's false. So eventually there's a fee that's iterating over some value. The fee has no fall in value and no back end value. It's merging two dead things. So it's the meat of 0 things, which is top. So I've computed top, even though I'm doing a standard forward flow analysis. Then later on, I merge top with some other random value, and I want to do something, add of 17 and top and shit like that. Eventually it flows down to a live path and a dead path, and the top comes on the dead path, and the fee says it's dead. I'm chopping that path off, and then it's all dead in the graph, and it rolls up and goes away. But in the middle, I get tops floating around as the meat of 0 things. Sorry, Darrick, I cut you off.
No, that's fine. Yeah. So in this system, I've got, like all the integer constants would be sort of lined up here.
Right.
And then I've got any and unknown, and then things get a bit more complicated.
Well, you broke out ranges
that I'm trying
and
to
signed and things.
deal with is signed versus unsigned, because I have to treat them a bit differently.
Yeah.
In the risk, I can just say, yeah, they're all signed. That's fine. But on the in the PE array, it's like sort of I have to know. And
okay.
So I was thinking that maybe I move within the lattice. Like I can say that, you know, an unsigned is above signed, maybe.
So So when I did this in C2 in Java land, what I did was I had ranges, and the ranges have an obvious inverse implementation, which is really sweet. It's really simple. So you get the dual sort of easily. But the operators varied, whether they're unsigned or not, and they varied about whether they sign extended or didn't, according to whatever. But that was done by the transfer functions and the nodes in the graph, not in the lattice. I did not have to represent signedness in the lattice.
Oh, really?
Yeah.
So how do you deal with a range from, you know, -1 to 1?
That's a range. I have the range.
So
So if you look at the range math in C2, you'll see there's a min and a max. And in the dual, you swap min and max. And math just works out for free. So it's really cheap to do this. So if I have a range that is an actual range from -1 to 1, the min will be -1, the max will be +1. Done.
Okay. And so, okay, I had a lot of complexity in mind trying to convert, you know, between, so if, you know, if you've got a -1 byte, and then you suddenly start treating it as unsigned, it turns into 255.
Okay, so here's where the transfer functions come in. If I have a -1 in memory and I load it, I'm loading it signed or unsigned. When I load it at that time, I say, oh, I'm going to treat it as unsigned. Now it's a 0 to 255, or it's a 255. And then the other guys just saw a 255. They never saw the -1. I never put types in the signedness in the types, other than the range went from 0 to 255, or the range went from -128 to +127, or whatever. The range consumed the sign bits.
So that transfer function is kind of like a node in the graph that's kind of like a reinterpret cast.
I never had to deal with in Java directly somebody casting a signed thing to an unsigned thing, but yeah, that's how it would work. Yeah, it would be a node that changes the type from -128, 127 to 0 to 255.
Yeah, so I do the intervals thing where, like, if the what's it called, if the min is bigger than the max, and you wrap around basically.
Yeah.
And in my setup, I don't type my additions or most of my operations. So like add just says it's an addition.
Right.
And then what ends up happening is that if I have operations that are signed and they get an unsigned range, they'll just like or actually usually it's if you have unsigned operations and they get a signed range, they'll just reinterpret it. And usually they'll just default to like, oh, we have the full range because we can't represent that as like a signed range or as an unsigned range.
Yeah. Okay. I mean, like I said, I don't get signed in the types. I get them in nodes. So
yeah, well, like an example would be that if I'm doing if I was doing an operation that was, let's say, I did like a load, then I signed extended, so it's going to be like a signed looking range. I might do some adds on that, so it's going to stay signed.
Hang on.
And
yeah, so hang on.
then I go to a compare, and the compare says I'm an unsigned compare.
Right.
I will just flip the flip the range and be like, I've lost information because I just can't do an unsigned or I don't have the accuracy I needed for an unsigned compare necessarily. Sometimes I do.
All right. So I think the difference here is that in Java bytecodes, I don't have signed and unsigned operations other than loads and stores, or loads. Stores just truncate. Loads sign or don't. And in fact, they don't. Well, they do. A couple of them do. But people mask, and I just fold that into the load. So when I go to hardware, the x86, I'll use various versions of loads if people did masking in the Java bytecodes.
Makes sense.
I do have an unsigned compare versus a signed compare. because the unsigned compare is used for range checks. You can't write one in Java bytecodes, but you can get it out of range checks. So I'll do an unsigned compare, and he'll interpret the input as a signed range from minus to plus, minus, int min to int max. There is no 64-bit signed versus unsigned distinction in Java, in the lamb Java, but I know in C you do have that.
Yeah.
Sure. So yeah,
I mean, I would argue there is a distinction, which
like
is that unsigned doesn't exist.
All right, one at a time. So Yasser first.
So yeah, push comes to shove. If you ever have an operation that like wants to work on like the sort of min is the smaller number unsigned and max is the bigger number signed or unsigned, then you can always like just default to like, oh, we take up the full range because we just can't represent this as an unsigned range.
Yeah.
But usually you don't have that.
Okay. Right, but the point is there's an easy transfer function which looks at the mcup and says, I'm going to treat this as if it's something. Oh, it's not what I was hoping to find. Boom, I blow up. I lose probably minuscule amounts of precision. And it's done. Yeah. Okay. And then Aaron, you were saying something?
I was saying Java does have a distinction between signed and unsigned ints. Unsigned ints don't exist.
Yeah, exactly. But people will do load along as an int as a long, and then cast it with sign extension or cast or mask it or whatever, and they'll fake it in a long as an int that has been 0 or sign extended. And big integer decimal, big integer math is full of this stuff.
Yeah.
So there were a million billion places where I did sign extension and 0 extension and truncation math, and C2 is trivial optimizations using just those ints that were not signedness. And that all worked out.
Is the reason you feel like it's worth having a distinct type for numbers that aren't 0 just because of divide by 0?
Say again, Aaron?
Often when you're describing numbers, you have a distinct type for numbers that are non-0.
Oh, in AA? Not in C2.
Yeah, is that just for divide by zeros
being
able to be peephole away?
It was me doing experimentations with a null value, which was ambiguously pointer null, integer null, float null. And it was a way to claim there's a uniform null concept. And to make that happen, I had to carry null sharpness through all the subdomains. So the floats and the ints and the pointers all have a null and not null knowledge in order to keep the lattice symmetric and associative and commutative and all the properties I wanted out of the lattice. So that was the reason it happened. I wanted the fancier null. If I got rid of it and I say I have a pointer null, it's separate from the integer null, then that would go away.
And if somebody wants a nullable integer.
When you say knowable integer, I don't know what that means.
If I want to have a value that could be any 32-bit integer or null.
Yeah, I don't have a distinction specifically. If you're any 32-bit integer, you included a null.
Okay.
This is not like I'm doing some sort of wrapped integers where I have a null versus a wrapped capital I integer. No.
Yeah, every once in a while I run across something that's like a result of an option.
Right. So in my head, those are things like I want to have a concept of I have or I don't have something. And then if I have something, it has more interesting stuffs to it. And in the land of pointers, that's usually I have a null, I don't have a thing, or I have a pointer to a person who has blah, 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 blah. In the line of integers, I typically don't have I have something or I don't on an integer. But if I were to do so, because I'm doing high performance math and a H2O startup, then I secretly behind your back picked a value that represented I don't have an integer, the not available. And I varied which value it was according to how the compression encoding worked. When you went to go get a value out of an array, an int array, under the hood you never saw, when you loaded a value, I checked, was it not available? And I did different things according to that. So if you attempted to do something with a not available value, each of the sub operators had a decision to make about what it meant to do something with a not available, but they all could tell. And one of the common things
Yeah,
was
the
it would
version
bark
of
with
that
you.
I've run across had two magic numbers.
Yeah.
One that was this is the null number,
Yeah.
and one that was this was one of the two magic numbers that you got unlucky enough to hit. Go to the look aside hash table and find out what was actually in this address. And
Yeah,
that
and
hash table had a mapping from the address at which point you found the magic number to one of the two magic numbers.
Yeah, I got to do that a little easier in H2O. It was the compression varied by
because you can actually look at the entire set before you start and go, this one didn't happen.
Yes, look at the entire set. I picked one you weren't using. Yep.
No, they like, is this a tweet ID or null thing?
Yeah. Right.
You really don't want to spend an option. You want to fit in that.
You want to fit in that thing. So you wanted to pick a magical. I wasn't one of these. Yeah. All right. Yeah. Anything else? Wrap it up here.
Yeah. I mean, I'm just looking at, so I had a simplification to this whole nest that I had in the middle there, and I just sort of, while you guys were talking, put it in.
I see, yeah.
Which was, I actually extracted the domain, like which system the integer is actually going to be landing on.
So domain means
a separate little lattice.
Or PE.
Yeah, so it's either running on the RISC or it's running on the PE array.
Okay.
But a lot of times I just write, X plus Y type of stuff, and we don't know. So it starts at any.
Yeah.
And then if some operation happens, like, do I do like control flow on it, then I know it's going to be in the RISC. If I do something PE specific, I might know it's on the PE.
Yeah.
And then basically, I think this is a sort of interesting case where I think if I'm still on any, by the time I compile, like by the time the compile is done, then I can just choose.
Mm-hmm.
And then if it's unknown, it means that I've mixed the logic and it's actually invalid.
Oh, that's interesting. That's inverted from the usual story. Sure.
Yeah, but yeah, that's what I was kind of thinking. I was kind of wondering if I'm wrong, but I think it works out.
Well, sounds right to me.
Unknown means you need to be on both. You must be on the union of your two hardwares. That's not a thing.
That's not a thing. So it's an error. Right.
Yeah.
But in the land of AA and simple, I guess C2's typing systems, if you mix pointers and ints, the meat of them goes to bottom. That's a type error.
Yeah. Okay.
So I think that's entirely sane.
Okay. Yeah. That's sort of the same idea. So that's good. So I just sort of made this a nested structure, and it cleaned up the whole definition.
Yep.
Then, but what you're saying is also I can get rid of the signed unsigned structure.
Yeah.
Because I was thinking maybe I needed one of these for that too, but not. And maybe I just have sort of cast nodes where I need them. So I say, oh, actually, I'm going to treat this as sign. It just shifts the range.
So well, I kept it in the operators internally cast. Yeah, but I guess you could have a cast that said, like, I didn't want to have a type system. I didn't want to have signed and unsigned in the integer type system at all. That simplifies a lot of things because
it made it very confusing.
I'm sorry?
It made it very difficult and confusing because I had all these like crazy exceptions in my, calculating the value of my types as it was like figuring out, oh, if this is negative and that's like,
okay,
this is
you might look at what C2 did here, because it turns out that due to sort of easy, I have a min and a max, and the dual just flips them. All the maths for like add and multiply and subtract all just do the normal thing, and they work out. It's a little kind of crazy fun. It's not obvious, but you max, so like, you add them
with
up.
You add the mins and you add the maxes, and
yeah.
And there were some where I had to cross join.
I had to look for places where I overflowed and just force the situation out. For some operators, there was an overflow test that said, "Oh, I give up."
Yeah.
Yeah, there is a funniness that in int32 plus an int32 is in 64 because you need Java, one more bit. So
right, no, in Java, if you add two ints, you get an int result and they wrap. And that's just the spec for Java.
And that's how treating it to. And
That's
in
not the
fact,
spec
I
for
have,
addition, but sure.
No,
Yeah.
I didn't say it was spec for addition. But if you add two 64-bit things in Java, they wrap and then you go to big integer, right? Yep.
Yeah. Okay. Well, anyway, that's where I'm at. So that
Nice.
was helpful. Thank you.
All right. Well, I think we're going to wrap it up.
This was a good one for me.
Excellent. Well, I think it was good for Jindu. I hope it's good for everyone else. Nice seeing people, and until we meet again. Bye.
Bye.